Section 7.3, composition of functions. So again, like everything in Chapter 6 and Chapter 7, a lot of this we already know. We understand how to compose functions. What we're going to do is update our our definitions to set theory and look at some proofs and some problems dealing with compositions of functions and set theory. So we have two things to do in this section. Number one is just redefine compositions. And number two is to look at composition and how it pertains to injective and surjective functions. So this is composition and injectivity and / or surjectivity. All right, so let's redefine our composition of functions. So we are going to let f be a function that maps a set x to y, and g will be a function that maps y to z, and these will be functions. Then a new function g circle f maps x to z. This can be defined by the following rule. So g circle f of x equals the classic definition g of f of x for all little x in the set x, and this is called the composition and is called, scoot that up a bit, the composition of f and g. All right, so little changes here and there, but for the most part, this is our rule for composition. Now, our book, I believe, talks about composing f and g as this. So you compose f and g in this order, but in all honesty, if you think this is the composition of g with f, because that's what my brain wants to think, that's fine. And if you're getting a little, hung up on the homework, just take a look and make sure that they don't mean for it to be g circle f versus f circle g, and just keep that in mind. So let's go ahead and look at an example working with compositions as sets or as functions on sets. So we're going to let f map integers into integers, and g is going to map integers into integers. And these are going to be defined by f of n equals n plus 1, and g of n equals n squared for all integers n. So we're going to look at two things. We're going to do two things. We're going to find g circle f and f circle g, and then we're going to determine, is the function g circle f equal to the function f circle g, using our new definitions of function equality from the previous lesson. So let's go ahead and take a look at this stuff now. So part A should be relatively simple. I would again suggest pause the video, form your compositions. You shouldn't be able to. We all can do this. We've composed functions. So g circle f is g of f of n g of n plus 1, or n plus 1 squared, which will be n squared plus 2n plus 1. And f circle g is f of g of n, or f of n squared, which is n squared plus 1. So these are our two function rules for g circle f and f circle g. Part B now, again, we're thinking about the set theory definition of functions being equal. So we want to think about f circle g and g circle f as their sets, or as their what they map to. So f circle g of n equals g circle f of n. So if these are equal for all n in Z, then I don't know why I keep switching order here. G circle f equals f circle g, or g circle, or f circle g equals g circle f. But we need all of their codomain values to be the same for the inputs. So we can look at just one example. Again, we've talked about this. It's much easier to disprove, or to start by thinking about disproving a universal, because that's essentially what we have here, because we need this to be true for all n. It's a lot harder to show that that's true for all n, because we know there's infinite integers. So just pick any n value you want and see if you can get an idea of whether this is going to be true or false. And again, I'd recommend you pause the video and see if you can come up with your own value. Now, I'll go ahead and give you a clue. This is not going to be the case, and we probably already know that just from what's happening here. But come up with your own counterexample. My counterexample, as you know, I like to keep things simple. I'm just going to look at 1. So g circle f of 1 and f circle g of 1. So we're using our new rules. So this is 1 plus 2 plus 1, which is 4. And f circle g is 1 plus 1, which equals 2. Well, that means that this is not the case. So we know that g circle f does not equal f circle g. Now, some of you may have, as I normally do, chosen 0 as your value that you checked. Well, if you pick 0, 0 plus 0 plus 1 is the same as 0 plus 1. And so we run into some issues. And, well, not some issues, one issue, in that we get f of g of 0 equals g of f of 0. And then we would have to look at another one. So we've talked about this. When you're trying to decide if something is true or not before you start proving it, don't just check 1, at least check 2. I'd recommend you even check 3 different instances. Now, if you check your first one and you have a result like I have here, where they're not the same, well, then you don't need to check 2 and 3, because you know you're going to fail once, which means you don't have equality all of the time. So, just like in 7.2 and 7.3, there's going to be some homework problems that ask you to look at equality of compositions, and you want to be thinking about this definition where your functions are equal if the values are equal for every n value, every integer or every domain value. So now I want to talk about a very specific composition. So this is compositions with an identity function. Identity function. So if we have a function, f, that maps x into y, so if f is a function, Now, I do want to pause here. I know I wrote this before, and I probably wrote this in the last section. The reason we have to say this is a function is because even though we're using f, it's just the name, and the way that this notation works is this is just saying that we have a relation or a mapping. We map elements of x into elements of y. And so you can really replace this as saying if the relation f is a function, and then blah, 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 whatever we're going to write next. So that's why I keep writing if this is a function. I know we're used to, if you see f as a mapping, we usually only use that for functions, but not always. And so since we're in a very strict logical class in discrete structures, we're going to be doing things properly, and that's the only reason why I keep writing it like this. So if you've been thinking, why does he keep doing that? That's why. Okay, so if f maps x to y as a function, and I sub x is the identity function on x, and I sub y is the identity function on y. Identity function on y. Remember that I sub x identity functions map into themselves by I sub x of x equals x. And we can write a similar one for y. I sub y maps y onto itself by I sub y of y equals y. And so if we have our identity functions, then when we compose f with I sub x, this is f of I sub x. Well, this is just going to be f, because our identity function takes x back to x. So really we're saying f of x. Well, that's just f. And if we compose the other direction, I sub y composed with f, this is I sub y of f. Now, I sub y is y is y. So this is really just y. Now y is what we map to from x, so this is also just equal to f. And a lot of times you'll just see this. Because again, if we think of f as its set of values that it maps to, its image, then all the elements that it maps to in y get identified. And if you're composing f with y, f is a set of y values, because that's where we end in. We take x's into y's, and then we just identify those exact y's with the identity function I sub y. So this is something that we've seen before. If you just think about any composition you've ever done with the linear function f of x equals x, anytime you compose x with another function, it is just the identity function for the reals. So it works the same way. One thing we do need to key in on is the order. We have to make sure when we compose, since we know that, where's our composition page? From our definition, the way we compose things, when you compose, your codomain of your inner function needs to be a subset or equal to the domain of the outer function. So we can't do, in this case, in this example, or in this definition, we cannot compose f circle g, because f takes elements of x into y. G takes elements of y into z. So that means we'd be plugging y's into f if we did f of g of x. All right, I take that back. Scratch that. We'd be inputting z elements into f. Now, if we know that Z is a subset of X, then that can work. But we don't always know that, and we can't assume that ever unless we're told. So you have to make sure that when you're composing, you only compose correctly according to domains and codomains. So your outputs of the inner function need to be in the domain of your outer function. And with real numbers, we never worry about that because real number functions map reals to reals. And so in this last example, we made both compositions because both of these functions mapped integers to integers. So we can construct both. But there's going to be times in the homework where you can't compose both versions. If our G up here mapped integers to reals, we could do G of F, but we couldn't do F of G. And so we just want to make sure that we are keeping track of our domains and codomains when we're forming compositions. So we want to talk about compositions with functions and their inverses now. Compositions with inverses. Now, I know, again, that we all know how to compose inverses and what happens when we compose inverses. We just want to update our definition to set theory and look at a problem in that vein or under the scope of set theory, and then look at a couple properties about what happens if we assign, let's say, surjectivity or injectivity to an inverse or the given function. Now, one thing that doesn't usually get stated in the real number situation is what our function needs to be. So if f maps x into y is a bijection, meaning it's injective and surjective, so one-to-one and onto, with inverse f inverse that maps y into x, then f inverse composed with f becomes the identity function of x, or on the set x, and f composed with f inverse becomes the identity function on the set y. So we need a bijection to do this. Now we'll talk about that in a second here. But remember, these are functions, which is why we're writing them as the identity functions, I sub x and I sub y. If we get to the function rule, this says f inverse of f of x. F of x we know is equal to a y, so this is f inverse of y. And f inverse of y takes us back to x, and that's exactly what I sub x of x does. It maps the x value that we took back to itself. And that's what we've done here, because this x value and this x value we know are the same. Same thing for this other function, f of f inverse of y is f of x, since the inverse takes y's to x's, and f of x takes x back to y. And this y here is the same y that was in here, and so we've just identified, which is exactly what I sub y of y is. So let's talk about why we needed a bijection. So we know we need our function to be injective to even have the inverse in the first place, right? We have to pass that horizontal line test like we would have done back in algebra, but injective functions are invertible. We need the surjective property for our function when we take f inverse composed with f. So the reason we need this to be surjective is in this step right here. So f inverse of y will take y back to x. Now, if f is not onto, that means that there's some y's that don't map back to x. Or in other words, there's some x's that never get to the y's. But f inverse can take any element of y back to x. So now what happens if this y is one of the things that doesn't get mapped to if f is not surjective or not onto? Well, then this is undefined, which means that our composition fails and our domain now is different, or our image is different, because now we have an x that's undefined. So that means that we never get to this step, which means we never get to this step. And so our idea being here is that we want to eliminate all of those cases. So we need that bijective property of our function f. Now if f that maps x into y and g maps y into z are injective, well then G circle F is also injective. So you could think of this as a useful little property. I've got two of them here. And if F that maps X into Y and G that maps Y to Z are surjective, then G circle F is also surjective. And it's this second property here that our inverse property relies on. So if we're going to have this property, this f of f inverse equals itself, well, then we need to take the input and get to the same input. But if we don't have a surjective composition, f inverse of f, if that's not surjective, so you can swap out f inverse for g here, if this isn't surjective, then we can't get back to every single x, because there's going to be some x's that we can't plug in. And that's why we want that bijection. So let's go ahead and prove this second property since we've been talking about it. And so let's prove actually, let's not do a proof. Let's do something more fun. Let's find some errors, or one error. Find the error or errors in the following proof. Instead of having a write proofs, this is a way I can be interactive even though we're not physically interacting right now. So I'm going to write a little proof. This is going to be for this second property. If F and G are surjective, so is G circle F. So I'm going to write a proof. When I finish writing the proof, you should pause the video and see if you can figure out where the error or errors are. And then I'll walk through them with you. So the proof is as follows. So for all y in big set y, there exists an x in x such that f of x equals y. For all little z in z, big set z, there exists a little y in big set y such that g of y equals z. So I'm still working under these definitions, f maps x to y and g maps y to z. I just didn't write it here. So I have these two lines. So g circle f of x equals g of f of x, which equals g of y, which equals z. Come on, paper. Do what I want you to do. Thus, G circle F is on 2. So that's the proof that is submitted. I want you to now pause the video and think about, why is this proof wrong? And I will tell you there are 2 errors in this proof. And one of them is a structural error, and one of them is an actual fallacy that we've talked about. So pause the video and think about what's happening here, what is this proof actually saying, and what is this proof assuming? Okay, so if you're listening now, you've come up with your answers. So the first structural error that we have is that when we start to prove surjectivity, we want to show or prove, we need to prove for all z in z, there exists an x in x such that g of f of x equals z. So we need to start with an arbitrary z. In big set Z. That's how we always start surjective proofs, is you take an element out of your codomain and you show that you can find an element in your domain that maps to that. This proof does not do that. For one, it starts with arbitrary element of y and an arbitrary element in Z. Now we don't need an arbitrary element of y. So that's the structural error, is we're not quite starting in the right place. The second and the bigger error here is a logical fallacy, and that is jumping to conclusion. So there are actually 2 instances of jumping to conclusion. Going from these 2 lines to here is a jump, and going from this line to here is another jump. So let's talk about the first one and why that's jumping to conclusion. And some of you may be correctly identified is that the first 2 lines are just definitions. These are just definitions of surjectivity. Or of surjective. Because we know that f and g in this problem, in this proof, are supposed to be surjective. So this is just restating, yes, f is surjective, g is surjective. Now the reason this is jumping here is that the x, the y, and the z in these first 2 lines are all arbitrary, because these are just general definitions. So x, y, and z in lines 1 and 2 are arbitrary, which means when we get to line 3 here and we start actually looking at a value, the y here is not this y, and the x here is not this x. So y in line 1 does not equal the y in line 2. We have no reason to think it should, because we just restated definitions in line 1 and 2. Remember, anytime you start doing an actual construction proof, as we talked about, surjective proofs are constructive proofs. You are picking the correct domain value that gives you that codomain value. So now you've selected an arbitrary z, and you're saying that this x gives this specific y. Well, this x and this y cannot be the specific ones here. And so these aren't the same. So this proof is In the book, I believe, if I'm not mistaken, I would suggest that you go take a look at it to see how it changes. Now, you do need all of these lines. All of these lines appear in the correct proof, but there's more that's needed here. We need to fill in the details. So this gives us general definitions. We can use these to say, for this x, we could call it x1, there is a y1 such that that equals z. Well, but we don't want to start there because that's not what surjective is. We need to start with this z and say that because g is onto, there exists a y1, that g of y1 equals z. And because f is onto, there exists an x1 such that f of x1 equals g of y1. And then we can make this long statement here. So there's some pieces we need in there. And so this proof would be incorrect. And that will be the end of 7.3.